So the next chapter is about differential of multivariable functions. So now we really need to change our idea of the derivative. So what did I tell you about the derivative of single variable function, or differential, the meaning of differential? So there are many meanings. So first one was the rate of change. So in single variable case, to recall the meaning of f prime a, okay, for single variable function sending r to r. So it's different from multivariable function. Here we are talking Rn to R or some Rn to Rm, okay? So first meaning was the rate of change, that if you have a change of y, is approximately equal to the slope or rate of change times the change of x. Okay? The second was slope. So if I have tangent line at the point a comma f of a, then this is my equation of tangent line, which has the slope of f prime a. Okay? And the third one, I said third one is the most important part, which is fx minus some linear function when x goes to a is going to be 0. Here, this is your Lx, okay? This formula is Lx. So what does that mean? So it means that whenever you have the differential, it means that you have some linear function given by use of this differential, and this linear function is an approximation of value of function, and the error of that approximation goes to 0 much faster than the speed of x goes to a. That's the meaning of differentials of single variable case. So now we are now in the multivariable situation. So the simplest multivariable function we can think of is two variable function. So let's think about the simplest case. In this case. So I want to generalize all this meaning to apply to this case. So think about the rate of change. Okay, I need a change in x and y. Well, x here is here, but y is not the dependent variable here. Y is also an independent variable. So when I change something, I change x and y. I can change x and y independently. But in the rate of change situation of single variable case, we have one variable changed and the dependent variable changed accordingly, right? So one way you can mimic this meaning or extend the meaning of this rate of change to two variable case is that we only change the one variable and fix the other variables. So suppose we fix x to be x0 and change y only. So this change of y will be denoted by delta y, and this will be the change of input. And same meaning will apply to the delta y. So y is not dependent variable, it's input variable, right? So it's a change of input. And then the value of z, which depends on the function, changes by delta z. So what we want to extend this meaning is I want to relate something with multiplying something on delta y so that I can retrieve or approximate the change of the value of function. So I want to know what this is. So let's think of it this way. Since I fixed my value of x, so value of function only depends on y, so it's only one variable as an input. I can consider it as just a single variable function, right? And what I'm doing here is just looking at the output variable, which is z, and see how that changes according to the change of y. So it's actually looking at the single variable function. So I can say that change of y times the derivative of this single variable function is almost equal to the change of z, right? So now I need to think about the meaning of this a. What does that mean? Okay, so a is value of a, but what I'm actually doing here is I also consider that x has a value. It's only that it's fixed at some moment, but I can change that value too, right? So I don't ignore the existence of x. I simply fix my x value. So I need to take that account too. So I need to mention that x is also value at x equals to 0. But the situation is that I'm changing the y around a, but not changing the value of x. So by this meaning, this is called partial derivative. We call it fy x0a. Okay? So it's called the partial derivative. Okay? So can you do the same thing with x? So for example, fixing y and change x. You can do similar, but not the same thing. It's kind of happening because when you change y, you get the different change of z. And when you change x, you have another different change of z. So it's going to be different value. So here is the definition of partial derivative, more formally here. So maybe not definition right now. So just remark. So f of x, x0, so a, y0. So I just give a different symbol here to indicate that y is fixed here, is the rate of change of the single variable function f of x, which is fx, y0 at x equals to a, and f of y is same thing of f of y, which is x0, y at y equals to a. Okay, so that's one way you can generalize the meaning of the differential of a single variable function to multivariable function by using the partial derivative. So now let's think of this another way. So it's also extending the meaning of the differential as a rate of change. But now, since our two-variable function is a map from two-dimensional point to, let's say, one-dimensional line here. So if I have a point a comma b, right, or let's say x0 comma y0, then the whole point is that I want to change the input. I want to talk about the rate of change as my input changes and see how the output changes accordingly. So in these two examples, what I did is in this case I fixed y. So I changed only fixed y. I changed only x-axis. I changed the x values. So I'm moving along this horizontal line, passing this point. And also, in the second case, I'm changing the y value only, so I'm changing in the vertical line. But that's not the only way I can change it. I can choose any direction. So let's say this is my arbitrary two-dimensional point, and I want to change my point in u direction. Then what I want is how fast this function changes, the value of function changes accordingly. So let's define another function, let's say f of t, to be the point x0, y0 plus t times u vector. Okay, so here I'm adding a point with a vector. Doesn't really make sense, but what I'm saying here is considering this point vector, a point as a almost position vector, because the coordinates are the same. So more like I'm taking a vector, position vector, pointing to that point and adding to the point, adding another vector here. So I'm from the origin, move up to here, and then moving by t multiple of u vectors to get somewhere else here. Okay, So what I'm doing here is if I change a little bit in this direction, how fast the function value changes. So I want f prime 0. So this is the rate of change of f x comma y as xy changes infinitesimally small from x0, y0 in the direction of u. So this is called the directional derivative. And if I have this as a notation, then it lacks information about what point am I looking at the change of function and in what direction am I changing the point. So there's another notation for this. So directional derivative is defined this way using the function f defined that way, but the notation is this. We have d, capital D, stand for derivative, and the subscript u indicating the direction of the movement, and the point indicating at which point am I changing the input, and the function symbol here. So that's the directional derivative. So you can see that these two cases are very special case of directional derivative. So f of x is when u is the horizontal vector, which is 1, 0, and fy is when u is 0, y, which is vertical vector. So partial derivative is just special case of directional derivative. And this is one generalization of the meaning of the differential of single variable function to a multivariable function. So let's talk about the second case, tangent vector, or tangent slope. So if you have a single variable function, the graph is linear, which means it's a curve on two-dimensional space, so you can find the tangent line that touches the curve. But when you have the graph of two variable function, it's a surface, right? So it's a z-axis and xy-axis. Let's say we have a point x0, y0. I want to do the similar thing as we did for the tangent slope. So tangent slope is determined by the tangent line. So here, if I want to do the similar thing, what I want is to have a tangent plane, right? Here's the surface, and here's the point am I interested in. And it's a three-dimensional point on a three-dimensional surface. I want to draw a tangent plane that barely touches the surface at that point. So if you find a tangent plane, then you may say, oh, it's differentiable. It's somehow the slope, whatever that slope is, of the tangent plane will be somehow related to the differential of the function. But it's not clear. It's not clear yet, but let's think of this way. How do you determine the slope? How do you even define the slope of tangent plane? So in the tangent line, the slope is a slope, it's just a number. But in this case, you want to also say the plane is tilted in some direction. So how do you explain that? How do you explain the direction of this plane? What do you need to explain the plane, the face, the direction of the planes here? Yeah, which vector you want to choose? So there are infinitely many vectors inside the plane. The most effective way of describing the direction of your plane is having a normal vector, perpendicular vector, right? There's only one. If you normalize it to one unit length, one vector, then there's only one. Well, maybe there's another one in the opposite direction, but that's almost same. So let's say we have n. So let's try to find out this direction, the vector direction of this normal vector. So if I have two vectors on the plane which are not the same direction, which are not parallel, how do you compute n? Yes, cross product, right? So V1 cross V2, right, it's one way you can get the normal direction of the plane. And I need to find out two vectors, V1 and V2. What's the easiest way to get V1, V2 in this case? So I want V1, if I extend it to that direction, I want the tangent line that touches the graph of the function. And also I want to do the same thing with the V2. So one way you can do that is make the movement of your original point x0 and y0 in direction of x and y, okay? So suppose that you're moving your point in x direction. So you're here and moving along minus x and x here. So then accordingly, you will move your point on the surface along some curve on the surface, right? So there's a curve on the surface. And let's say this is C1, t. So suppose that t is the time. Okay? So at time t equals to 0, let's say the point is at the x0 and y0. I want to know how fast is the point is moving along the surface. So then this speed of movement on the surface will be my tangent vector on that point, of that point. So at C1t, let's say this is xt, that's not xt, so it's x0 plus t, comma y0, because I'm not moving along y-axis. And if I'm moving along ct, then to find the value, I'm just plugging this formula x and y into the function to get the value, right? So this is f x0 plus t, comma y0. So, and this, in this three-dimensional point on the surface, the coordinate will be x0 plus t, y0, and f x0 plus t, y0, right? So this is c1 tilde t, because I put tilde to distinguish that it's three-dimensional curve. So just imagine this is a physical experiment. You have x and y and z coordinates according to the parameter t. I want the speed. So each coordinate has a function, is a function of t, time, right? So in order to get the speed of each coordinate, you take the derivative of that formula. So what is the derivative? C1 prime t. So first formula is just the function of t, right? So when you take the derivative in terms of t, you get 1, right? You're moving along x-axis is the unit of speed. And how about the derivative of y? There's no t, it's constant. So when you take the derivative, the speed is 0. You're not moving, right? And how about the third one? So if you see this, there's only one variable changing, which is t. Right? It's not anymore two variable function. It's just one variable function. And it seems similar, something we saw before, right? We're only changing the x coordinate, right? We're only changing the x coordinate. So you can imagine that this x0 plus t is almost just some value in x, and we're taking the derivative of this one variable function in terms of x at t equals to 0. So this is the partial derivative at x0, y0, right? So let's do the same thing with the y coordinates. So pretend that we have movement along the y-axis, c to t, and now in this case it's x0, which is fixed, and y0 plus t is the second coordinates. And when you do that, so let me erase a little bit here. So when you take the c2t tilde, which is the three-dimensional coordinates of the curve on the surface. So curve will be something like this, and it will be x0, y0 plus t, comma, the last coordinate, the z coordinate, is going to be x0, y0 plus t. So if you want to take the speed, you take the derivative, so this is 0. I want the speed at this point, 0, 0. And look at the first coordinate. There's no t. It's constant. When you take the speed, it's 0. It's not moving. And the second one, it's 1. And the third one is fy. So this is, let's say, v1, and this is v2. Let's take cross product. So you have three-dimensional vectors, and you want to take the cross product. Do you remember the formula? The formula is E1, E2, E3, and you get the three coordinates of V1 and three coordinates of V2. So this is 1, 0, fx, 0, 1, fy. And you get the determinant. So this is minus f of x minus fy, 1. So it's not normalized, but you can normalize it later when you have it, when you have actual value. But the important thing is what the length of this is. It's about the direction. So if you see the formula, there's only two numbers that determines the direction. The last number, 1, is just constant number, right? It doesn't depend on what the function value is, or formula is. The first two, which is f of x and f of y, is what determines the actual direction of normal vector of the plane, right? So it's determined by what? Partial derivative. So if you want to find the tangent slope or tangent plane to extract the meaning of differential, so in some sense you want to find out how fast the function is changing, value of the function is changing according to the change of your point, then the tangent plane, it's kind of explaining approximately the change of the value of function. Because if you enlarge your graph closer and closer to that point, then the difference between the tangent plane and actual graph are getting smaller and smaller. So you can actually see the tangent plane itself is almost the same value of function. So in order to do that, all you need is just the two value of partial derivative, right? That's second way of expanding the meaning. And so the first and second are not complete meaning of the differential of the second two variable function and also multivariable function. The third one is the actual meaning of the differentials. And it's somehow related to this, what we discussed here, but we don't have time, so we're gonna finish it here. And as I announced, I'm gonna put up, upload the video about the next content. So take a time to watch it later. So if you have any questions, let me know after class.